Now, in this next section, we're going to be looking at confidence interval estimation for a single population mean. And we're going to be assuming, like we did in the previous section on hypothesis testing, we're going to be assuming that we know the population standard deviation, sigma. In a subsequent presentation, we will look at the more general situation where we don't know sigma and have to estimate it. But for now, we're still going to assume that we know the population standard deviation. So let x bar be the mean of a random sample of size little n from a normal distribution with mean mu and variance sigma squared. Now, the mean of a sample from a normal distribution has a normal distribution itself. The mean of its sampling distribution is the mean of the underlying population mu, and its standard deviation is equal to the standard deviation of the underlying population divided by the square root of the sample size. So what we're doing here, we are standardizing x bar by subtracting off the mean of its sampling distribution and dividing that difference by its standard deviation. And we're denoting that again as z. So we know that this standardized version of x bar has a standard normal distribution. Now, because of that, the following result obtains: the probability that this standardized version of x bar, so we could just as easily put in z right here, right? The probability that capital Z, the standard normal random variable, is less than or equal to z sub alpha. By definition of z sub alpha, this probability is equal to 1 minus alpha. That implies that the probability that x bar minus mu over sigma divided by the square root of the sample size being less than or equal to z sub alpha is also 1 minus alpha. Now, we can do some algebraic work on the components inside the parentheses. What we would be doing is multiplying both sides of the inequality by sigma over the square root of the sample size. And since that term is positive, the direction of the inequality stays the same. Then once we do that, we add mu to both sides. And when we do that, we get the following equivalent event: that x bar minus z sub alpha times sigma over the square root of the sample size being less than or equal to mu. So what we're doing is we're rewriting the stuff inside the parentheses and getting mu on the side by itself. And so this is the result of that. And because those events are equivalent, they have the same probability. And so what this means is that the probability of getting a hold of a sample for which the mean x bar minus this quantity is less than or equal to mu is 1 minus alpha. And so this implies, in repeated sampling, and by this we're thinking about probability from the relative frequency sense. So this implies that in repeated sampling, the random variable given by x bar minus z sub alpha times sigma over the square root of the sample size will be less than or equal to the population mean mu this percentage of the time, 1 minus alpha times 100%. Now, another way to say this is that the mean mu will be greater than or equal to the random variable x bar minus z sub alpha times sigma over the square root of the sample size, 1 minus alpha times 100% of the time. And it's because of this, for this reason, we call the random variable given by x bar minus z sub alpha times sigma over the square root of the sample size, we call that random variable a 1 minus alpha times 100% lower confidence limit for mu. Now, once we calculate this, once we have our sample and we've calculated the value of this random variable, we say that we are 1 minus alpha times 100% confident that the mean mu is greater than or equal to this lower confidence limit. So the way that we can interpret this confidence level, 1 minus alpha times 100%, we can think of 1 minus alpha as the probability. Before we select the sample, it's the probability of obtaining a sample for which this random variable is less than or equal to mu. So that's how we can interpret this. And if we think about doing this over and over again, a number of times with the same population using the same sample size, doing it 100 times or 1,000 times or 10,000 times, then the proportion of times that we would get a sample mean x bar for which this random variable here would be less than or equal to mu, the proportion of the time would be 1 minus alpha. Or an equivalent way to say that, the percentage of the time that would happen would be 1 minus alpha times 100%. Now we can make a similar argument and conclude that the probability that this standardized version of x bar being greater than or equal to negative z sub alpha is 1 minus alpha. And then doing some algebraic work on the stuff inside the parentheses, that is equivalent to x bar plus z sub alpha times sigma over the square root of the sample size being greater than or equal to mu. Okay, so those two events are equivalent, so they have the same probability. And so this probability is equal to 1 minus alpha. So before we move on to the next slide, let me just point out that whenever you have a probability statement, you've got to have a random variable somewhere involved in the event that you're talking about. Now, mu is not the random variable. We view mu as a constant, and it's an unknown constant, which is why we're doing statistics to estimate it, test hypotheses about it, and so forth. So the random variable inside the parentheses is not mu. The random variable is x bar, all right? And when we add this constant to x bar, then the resulting sum is a random variable as well. So what we're talking about here is that the probability that this random variable here on the right-hand side of the inequality being greater than or equal to mu, that probability is 1 minus alpha. All right, so if we think about this from a relative frequency standpoint, if we were to think about doing this same kind of process, the same kind of sampling procedure over and over and over again, each time calculating the mean of the sample, all right, then adding this constant to that sample mean, then the proportion of times for which this random variable would be greater than or equal to mu would be 1 minus alpha. So this implies that the random variable x bar plus z sub alpha times sigma over the square root of the sample size will be greater than or equal to the mean mu 1 minus alpha times 100% of the time. Therefore, the mean mu will be less than or equal to that same random variable 1 minus alpha times 100% of the time. And so for this reason, we call the random variable x bar plus z sub alpha times sigma over the square root of the sample size a 1 minus alpha times 100% upper confidence limit for mu. Now obviously in an experimental situation, we're not going to be sampling over and over and over again like I was describing. We're going to do it one time. We get one sample, we get one sample mean, and we construct one upper confidence limit. Once we have that sample, and once we've calculated that upper confidence limit, we say that the language that we use is that we are 1 minus alpha times 100% confident that mu is less than or equal to this upper confidence limit. And the way that we interpret this statement, that we are 1 minus alpha times 100% confident, the way that we interpret that is that we know that we are using a process that has the probability of obtaining a sample for which this random variable is greater than or equal to mu, the probability being 1 minus alpha. So that's the way that we interpret this phrase 1 minus alpha times 100% confident. So we've looked at how to construct a lower confidence limit and also an upper confidence limit, each with a confidence level of 1 minus alpha times 100%. Now if we combine a lower and upper confidence limit, we can get a two-sided confidence interval. Now if we want the overall confidence level of the two-sided confidence interval to be 1 minus alpha times 100%, then the lower and upper confidence limits that we choose, or that we construct, will have to be each at the 1 minus alpha over 2 times 100% confidence level. So if we compute both a 1 minus alpha over 2 times 100% lower confidence limit for mu, given by this quantity here, and also at a 1 minus alpha over 2 times 100% upper confidence limit for mu, given by this quantity, and if we put them together as an interval, so this would be the lower endpoint, this would be the upper endpoint of the interval, then what we get is a 1 minus alpha times 100% two-sided confidence interval estimate of the mean mu. And what we would say is that we are 1 minus alpha times 100% confident that mu is somewhere in this interval. And so again, the way that we would interpret this phraseology here, 1 minus alpha times 100% confident, is that we know we're using a process that has a probability of obtaining a sample for which this two-sided confidence interval has a probability of 1 minus alpha of containing mu. But we're not going to sample over and over and over again. We're going to sample one time, compute one confidence interval. That confidence interval either contains mu or it does not. But we know that at the point at which we were about to sample the population, the probability of obtaining a sample for which this interval contained mu was 1 minus alpha. All right, so putting these results together, the formula for a 1 minus alpha times 100% lower confidence limit for mu is given by this expression here. The formula for a 1 minus alpha times 100% upper confidence limit for mu is given by that expression. And then the formula for the endpoints of a two-sided 1 minus alpha times 100% confidence interval for mu is given by each of these representations. All right, so let's look at an example. So using the information provided in example 3.3, construct the following confidence limits and then interpret them. So again, this is the example where we're filling 8-ounce jars with peanuts. We want to construct a 97.5% lower confidence limit for the mean weight of peanuts being dispensed into these 8-ounce size jars. We want to construct the 97.5% upper confidence limit for the mean weight of peanuts being dispensed into these 8-ounce size jars. And then we're going to combine the lower and upper confidence limits to get an overall 95% two-sided confidence interval estimate of the mean weight of peanuts being dispensed into these 8-ounce sized jars. Let me just point out that the particular interval that would be of interest here, because if we think back to that hypothesis test, it was a two-sided hypothesis test test A. So of the three types of intervals that we're looking at here, either a lower confidence limit alone, an upper confidence limit alone, or a two-sided confidence interval, we would want a two-sided confidence interval, and we could construct it directly. But what I'm doing here is I'm having us compute these lower and upper individual confidence limits first to show that if you construct a 97.5% lower confidence limit alone and then a 97.5% upper confidence limit alone, if you then put them together, what you get is a two-sided 95% confidence interval. So that's what I'm trying to point out by constructing these individual endpoints. So we saw that the sample mean was 7.89 ounces. And again, we are assuming that the population standard deviation of fill weights is 0.2 ounces. And again, the sample size was 16. And so a 97.5% lower confidence limit for mu is given by x bar minus z sub 0.025 times sigma over the square root of the sample size. So the sample mean is 7.89. The interval coefficient, the z value, is 1.96. We're assuming that the standard deviation of the population is 0.2 and the sample size was 16. And so when we evaluate that, we get a 97.5% lower confidence limit for mu of 7.792 ounces. Now, I don't have it written down, but I'll just state the interpretation of this lower confidence limit. What we would say is that we are 97.5% confident that the true mean weight of peanuts being dispensed is greater than or equal to 7.792 ounces. I'll say it again. We are 97.5% confident that the mean weight of peanuts being dispensed is greater than or equal to 7.792 ounces. Now let's construct a 97.5% upper confidence limit for mu. So the formula for that is x bar plus z sub 0.025 times sigma over the square root of the sample size. So again, the same values, we're just adding instead of subtracting this quantity. So 7.89 plus 1.96 times 0.2 over the square root of 16. And so we get 7.988 ounces. And so the interpretation of that endpoint alone would be that we are 97.5% confident that the average weight of peanuts being dispensed by the machine is less than or equal to 7.988 ounces. So that's the interpretation of that endpoint. We are 97.5% confident that the mean or average weight of peanuts being dispensed by the machine is less than or equal to 7.988 ounces. Okay, now the next thing I want to do is I'm going to use the formula for a two-sided confidence interval to construct a 95% confidence interval for mu. I'll interpret this and then I'll say a few more things about it. So the formula for a 95% two-sided confidence interval for mu is x bar minus plus z sub alpha over 2 times sigma over the square root of the sample size. And so that would be 7.89 minus plus 1.96 times 0.2 over the square root of 16. Now, why is this 1.96? Well, in this case, alpha is 0.05, but alpha over 2 is 0.025, and we saw that z sub 0.025 is 1.96. So the endpoints of the interval are given by 7.89 minus 0.098 and 7.89 plus 0.098. And so the endpoints we get using this formula for the two-sided confidence interval at 95% confidence level is 7.792 up to 7.988. And so the proper interpretation of this interval would be to say that we are 95% confident that the mean weight of peanuts being dispensed by the machine is somewhere between 7.792 ounces and 7.988 ounces. I'll say it again. We are 95% confident that the mean weight of peanuts being dispensed by the machine is somewhere between 7.792 ounces and 7.988 ounces. Now, the additional thing I want to talk about, notice that the lower endpoint of this 95% confidence, two-sided confidence interval, is the same as the 97.5% lower confidence limit for mu all by itself. And the upper confidence limit of this 95% two-sided confidence interval for mu, 7.988, is the same as the 97.5% upper confidence limit for mu alone. So this shows that one way to get, for example, a 95% two-sided confidence interval is to construct individual 97.5% lower and upper confidence limits for mu, and then put them together in the form of an interval. All right, now the next result is very useful for planning an experiment. On this slide, we have a formula that gives us the sample size required in order to obtain a given margin of error at a given confidence level. If what we're wanting to do is to determine how large of a sample do we need in order to construct a confidence interval that has a certain margin of error and a given confidence level, then we would use this formula. So again, we're assuming here that sigma is known. If it's not, we'd have to approximate it somehow. But let's assume that the population standard deviation is known. Then the margin of error for a 1 minus alpha times 100% confidence interval estimate of mu is this expression that we add to and subtract from the point estimate to get the confidence interval. Right? If you go back and look on the previous slides, in fact, let's do that. This is the margin of error. This is what we're talking about. And so we're going to denote that margin of error by capital E, let's say. And what we're going to do is we're going to solve this equation for n. All right, so solving for n, we get the square of the interval coefficient, z sub alpha over 2, times the variance divided by the square of the desired margin of error. So once we've determined the confidence level we want to use, which would determine alpha, once we've specified the margin of error that we want by specifying E, and as long as we have either we know sigma or we have a reasonable approximation to it, right, so that we can square it and get the variance, then we can determine the sample size needed in order to have a confidence interval, two-sided confidence interval that has a margin of error specified by E. So let's look at an example. So again, going back to this example where we're filling jars with peanuts, so how large of a sample must be used in order to estimate the mean weight of peanuts being dispensed using a 95% confidence interval such that the interval has a margin of error of only 0.05 ounces. Let's see what sample size would be needed. So here is the formula that we'll use, and we know that our interval coefficient The z-value is 1.96, so we would plug that in there, and we need to make sure to square it. All right, that's a common mistake. We are assuming that the population standard deviation is 0.2, all right, and so we'll put that in the formula, but again, we need to make sure that we square that as well. And then the desired margin of error is 0.05, so we would plug that in. And so when we do the calculation, we get a calculated sample size of 61.5. And because we cannot have a fractional sample size, we're going to use the next larger integer. Now, I say rounding up. What I really mean there is that we're not going to be rounding. If this was 61.2, we'd still use 62. All right. If we ever have a fractional value on a sample size calculation, we're always going to take the next larger integer. All right. So that's the material on confidence interval estimation for the situation where we know the population standard deviation. In a future lecture, we'll look at the situation where we don't know the population standard deviation and how we can come up with a confidence interval in that situation.